So we've looked at first order linear differential equations. What we're going to do is take our understanding of these and extend it and stretch it into starting to look at second order linear differential equations. Now this is a big topic. This kind of thing comes up, I can pretty much guarantee you, 99% of the exam papers that I've seen. So it is something we need to know how to do. And it's something that can be useful for applications beyond just simple mathematics, so in physics, chemistry, biology particularly. So we need to be able to solve this. Now the big issue with this is that there's two different types of second order linear differential equation, and within these types there's several formats the solutions can take. So what we're going to look at is we're going to look at different types of solution, different types of equation, and how we can handle these. Now first things first, we need to understand the difference between the two types. So imagine I've got this here, second order differential equation, and it looks like this. So it takes the format of a times second derivative of y plus b times the first derivative of y plus c times y itself equals q of x. Now I told you there's two different types, and that all depends on this q of x here. Now if this q of x is equal to 0, this type of equation is what's called homogeneous. If this q of x does not equal 0, so takes some format of a function, this is called non-homogeneous or inhomogeneous style equations. What we're going to do is we're going to focus on just the homogeneous to begin with, then we'll extend this to inhomogeneous later on. So we have to be able to understand how to solve this and how to get solutions to this equation. However, there is one rule from previous mathematics and previous bits of algebra that we need to just refresh our memory of, which we're going to use to apply it. Now this rule states that if y equals f of x and y equals g of x are two distinct solutions to the second order differential equation, then y equals f of x plus g of x is also a solution. So if this was the case, let's imagine I take y equals f of x first. What I would know is that a d2f by dx squared plus b dy by dx, sorry, df by dx, not dy by dx, plus cf equals 0 would work, but I would also know that y equals g of x, if I took it in that format, that I'd have a solution a d2g by dx squared plus b dg by dx plus cg equals 0 is also a solution. Now if I treat this like a column sum and I add them all together, what I get is that a d2f by dx squared plus a d2g by dx squared plus b df by dx plus b dg by dx plus cf plus cg equals 0. So I get that there. So if I then use the additive law of differentiation, take these, take a common factor of a, because these both have that, and then use my additive law from there, what I can then say is that a d2 of f plus g by dx squared plus b d of f plus g over dx plus c times f plus g equals 0 also works. So if I have two solutions, y equals f of x and g of x, if I add them together, I get a distinct solution to that differential equation. Now this is an important law to remember because it comes in handy for us when we're looking at the actual solutions. Now, if you remember back to first order differential equations, we knew that y equals a e to the mx was a solution there. So it's reasonable for us to consider it for a second order differential equation as well. So let's do that. So if I've got y equals a e to the mx, my first derivative, dy by dx, is equal to a m e to the mx, and my second order derivative, d2y by dx squared, is equal to a m squared e to the mx. So what I can now do is take this and substitute it back into my second order differential equation. What that will then give me, small a times a m squared e to the mx plus b times am e to the mx plus c a e to the mx equals 0. Now if I take e to the e to the mx out as a common factor of each of them, what I end up getting is am squared plus bm plus c, all in a bracket itself, times a e to the mx equals 0. Now, if I want this solution to work, it all depends upon this here. A e to the mx can never be 0, so all depends on this part here, am squared plus bm plus c being equal to 0. It has to be from that we get there. Now, if I take this and I was to solve it, so factorise it and solve it like you would a normal quadratic, we'd get two solutions. So we get a solution m equals m1 and m equals m2. So what that means is I would get two distinct solutions, y equals a e to the m1x plus b e to the m2x. So there we go, I've got two different solutions, a e to the m1x plus b e to the m2x. Now a and b, what they're done is they're used to distinguish two different arbitrary constants which could come from both solutions dependent upon which m value we've got within there. Now this equation here, this am squared plus bm plus c equals 0, this is what's called the auxiliary equation. This determines the type of solution that we can get. Now because it's a quadratic, we know that there are three types of solutions that we can get for a quadratic. Two distinct real roots, one repeated root, or two complex roots. Each of these has a different outcome and a different solution for the overall equation y. What we're going to focus on in this first case is we're going to look at when we have two real distinct roots. What that means is if I look at the auxiliary equation and I do b squared minus 4ac is bigger than 0, I know I'm going to get two distinct solutions for m, and I can then get my solution y equals e to the m1x plus b e to the m2x. Now I'm going to show you how the steps work for this. It's the same general steps every single time, you just have to make sure you follow them. So step 1 is we have to write down our auxiliary equation. Now this is actually quite straightforward because all you do is you look at the coefficients of each part dependent upon y. So this here's a coefficient of 1, this is -7, and this here's 10. So I can write my auxiliary equation as m squared minus 7m plus 10 equals 0. So now that I've got that, I can solve it like I would a normal quadratic. So I end up with m minus 5, m minus 2 equals 0. From that, I get that m is equal to 5 and m is equal to 2. They are the two solutions to that auxiliary equation. And what I can then do is substitute it in and actually get my solution. So that's the second stage. Substitute it in because I know that y equals a e to the m1x plus b e to the m2x. Now it doesn't matter which way around you put your m's, as long as you put them both in. So y equals a e to the 5x plus b e to the 2x. And that there is called the general solution. We've still got the arbitrary constants a and b, but we've got two parts of the solution. We've got our two powers, and there you go. If we were to substitute that in, we'd get a solution to the general equation. However, this obviously isn't enough a lot of the time. What we want to know is how do we get rid of these arbitrary constants a and b and get a solution with just numbers in it? Well, that's what we're going to look at now, because that is what's called the particular solution. So let's imagine I'm going to take that example again and I want to find the particular solution to it. In order to get rid of those two arbitrary constants a and b, what I need is two sets of conditions that I can substitute in. Now the reason being, I've got two things that I'm trying to eliminate and find. In order to do that, I need two conditions that it satisfies. So if you think back to the steps before, if we were to then do the exact same set of steps to get our general solution, I'd get m squared minus 7m plus 10 equals 0. So I'd get my m minus 5, m minus 2 is my two solutions to that. So I know that m is equal to 5 and m is equal to 2. Substitute them in, and I get y equals a e to the 5x plus b e to the 2x. So there you go, I've got my general solution. This is always the first step. We want that general solution before we do anything else in order to find the particular solution. Now I mentioned about getting two sets of conditions. Well, this is them. What we'll end up getting is one condition based upon the original function, where we get y is 3 when x is 0, and one based upon the derivative of the function. In this case, dy by dx is 2 when x is 0. We have to use these to eliminate the a and the b. So if I take the first part, the x and the y, and substitute them in, so let's call that 3, what I'll end up getting is a e to the 0 plus b e to the 0 is equal to 3, e to the 0 is equal to 1, so I get a plus b equals 3. What I then want is I want the derivative. So if I take dy by dx of this, what I'll end up getting is dy by dx equals 5a e to the 5x plus 2b e to the 2x. Now, I know previously we've said when we have something like this, 2 times an arbitrary constant, we just combine it to make a new arbitrary constant. But not in this case. A and b are their own distinct arbitrary constants we are trying to find. So we have to keep them like that. We can't combine them with the number. But what we've now got is the derivative here, so I can now use my second condition, which is this. So when x is 0, the derivative is 2. And if I substitute that in, what I'll end up getting is 5a plus 2b equals 2. So what I now have is two simultaneous equations here, which I can solve together, because I've got 5a plus 2b equals 2, I've got a plus b equals 3, and I can solve them, as I've mentioned, using the simultaneous equations method we covered back in S3 and 4. So if I multiply the second equation by 2 to get rid of the b's first, what I'll end up getting is 5a plus 2b equals 2, 2a plus 2b equals 6. Subtract them from each other in order to eliminate that. What I'll end up getting then is that 3a equals 2, take away 6, is equal to negative 4. So a is equal to negative 4/3. I can then substitute the a equals negative 4/3 back into any of these equations to find b. I'm going to go for this one here because it's the simplest. I'll end up getting negative 4/3 plus b equals 3. So I'm going to add that on. So b is equal to 3 plus the 4/3. So 3 can be written as 9 over 3 plus 4 over 3, which gives me 13 over 3. So what I can now do is substitute these back into this equation here, my general solution, in order to get the particular solution for the equation, which in this case is going to be y equals negative 4 over 3 e to the 5x plus 13 over 3 e to the 2x. So the a and the b in this case are fractions like that. If I wanted it in a particular form, I could maybe take the 1/3 out as a common factor if need be. Otherwise, we can leave it like that. Couple of points to note. First, we always want two equations like this that we can solve simultaneously. That's why we're given two conditions. We need them to get the two arbitrary constants. Second, make sure when you put your a and your b back in, they go with the associated powers that they've come from. So for example, my a e to the 5x, the a is always with the 5x. If I put the value for b here, so 13 over 3 e to the 5x, my equation would be wrong. It would no longer satisfy what I want because my constant is not associated with the correct power of the exponential. That's a key thing to remember because that's a key area a lot of people slip up on. We need to make sure constant and the appropriate powers are associated together. There's a few easy steps that we can use and we can follow to solve these. May seem a bit intimidating at first, but actually as you get more practice and you see the cases, it becomes a more second nature and a bit easier to use.